So in the last two videos, we talked about line spectra and how Bohr used the data from the line spectra experiments to build his model of the atom, to develop his model of the atom. In this video, we're going to do a couple of sample calculations relating to that model of the atom to hopefully give us a bit better understanding of what it's telling us. So we're first asked to decide whether we would expect more energy to be released when an atom relaxes from an excited state to the n equals 1 or to the n equals 2. If we go back to the diagram that we had on page 24, we can see that actually every single energy transition going to the n equals 1 is larger, which you see because there's a longer arrow on this diagram, compared to every single transition going to the n equals 2. Essentially, the n equals 1 orbital is substantially lower in energy than any other orbital. The n equals 2 is, of course, the next one up. The gap from 1 to 2 is much bigger than the gap from 2 to 3, which is bigger than the gap from 3 to 4, which is bigger than the gap from 4 to 5, and so on and so forth. Every single subsequent energy level is closer to the previous one than the gap before that. And so no matter where we start, we're going to release more energy going down to the n equals 1 state than we are going to any other state, including the n equals 2. So we were able to do that just based on understanding and looking at the picture. We didn't actually need to run any numbers. For the second example, we do need to run numbers. So here we're looking at being asked to calculate the energy and wavelength of the photon emitted when a hydrogen atom, and that's an important point, relaxes from n equals 5 to n equals 3. Why is it important that we're talking about hydrogen? Because that tells us the number of protons. So because we're talking about hydrogen, we're talking about an atomic number of 1, a plus charge of 1 for the nucleus. So let's go back to our diagrams and see, what does this look like on the diagram? So we are now looking at the transition from the n equals 5 to the n equals 3. So our electron is going to start up there and it's going to go down there. There is a change in energy associated with that. And the energy of our photon is equal to the absolute value of that energy change. If we are looking at emission of light, the delta E will be negative. If we were looking at absorption, the delta E, the energy change, would be positive. But either way, the photon involved has the same amount of energy. So how do we calculate delta E? Well, it's pretty straightforward. Delta E is going to be equal to the energy of the final state or the final orbital minus the energy of the initial state or the initial energy of the electron. So if we go back to this question, we're going from the n equals 5, so that is our initial orbital, to the n equals 3, so that is our final orbital. And so our delta E, therefore, is going to be equal to the energy of the n equals 3 minus the energy of the n equals 5. Recall that the energy of either of those is equal to negative Rydberg constant times z squared divided by n squared. Z is 1 because we're talking about hydrogen. So negative RH times 1 squared divided by n squared which for hydrogen will therefore be negative Rydberg constant divided by n squared. Don't forget that negative sign. It's important. So if we plug our values in here, then we have negative Rydberg constant divided by 3 squared minus negative Rydberg constant divided by 5 squared, which is the same thing as negative 1/9 of the Rydberg constant minus negative 1/25 of the Rydberg constant, or 1/25 minus 1/9 of the Rydberg constant. And so I have 1/25 minus 1/9 times 2.179 times 10 to the minus 18 joules. And when I plug all of those into my calculator, I get negative 1.550 times 10 to the minus 19 joules. And you'll notice that you expect most of your answers to fall in the general ballpark of that Rydberg constant. This is a fraction of the Rydberg constant. So the fact that my exponent is times 10 to the minus 19 is good. That means it's within a factor of 10-ish of the Rydberg constant. And when I look at the sign of my answer for delta E, it is negative, which corresponds to emission, which is what this question is describing, emission of energy as the atom relaxes to a lower energy state. So delta E should be negative. So I'm happy with this answer. It's negative as it should be. It has a magnitude that it should, that is consistent with what I expected. This is delta E. This is not the energy of the photon. The energy of the photon has to be positive, so it is the absolute value of delta E. So the photon has an energy of 1.550 times 10 to the minus 19 joules, and that is a positive energy because photons can't carry negative energies. So that answers part one of the questions. We have calculated the energy of the photon. Now we have to calculate the wavelength of the photon. We can do that using the equations that we've seen for light. We know that Planck's constant times the frequency is equal to the energy of a photon. And we know that if we're talking about light, then the speed of light is equal to the wavelength times the frequency. And therefore, the frequency is equal to the speed of light divided by the wavelength. And therefore, the energy of the photon is equal to hc over lambda, which means that the wavelength is equal to Planck's constant times the speed of light divided by the energy of that photon. And now I start plugging in values. So for Planck's constant, I have 6.626070 times 10 to the minus 34 joules times seconds, or joules per hertz. Either will work. Speed of light is 2.9979 times 10 to the 8 meters per second. And we divide all of that by the energy of our photon, which was 1.550 times 10 to the minus 19 joules. So my joules cancel. My seconds cancel, or my per hertz would cancel with my per second. And so when I plug all of those numbers into my calculator, I get 1.281 times 10 to the minus 6 meters, which is equivalent to 1.281 micrometers, or if you prefer, 1,281 nanometers. Either of those would be a good way of expressing your answer without having to use scientific notation. I'm particularly fond of the nanometers answer for this particular question, simply because I'm then asked what type of electromagnetic radiation this is. And I know that visible light is 400 to 700 nanometers. 1,281 nanometers is bigger than that, longer than that, lower energy than that, but still pretty close. And so this is therefore going to have to be infrared or IR radiation. The other question that we're asked to solve is to calculate the energy required to excite an electron completely out of a ground state hydrogen atom. So we've got some keywords here. Hydrogen atom, Z equals 1 proton. Ground state, N equals 1. The lowest energy orbital or state for any atom is the N equals 1. And then if that's our initial energy level, what is our final energy level? Well, our final energy level here is the completely out of the atom. So where's that on our picture? Well, this time we're not calculating n equals 5 to n equals 6. This time our starting point is the n equals 1, and our ending point is the not in the atom anymore. And so this now is our delta E here, going from n equals 1 all the way up to 0 joules. So in this case, our final energy is 0 joules. And we could express that as saying that n equals infinity, because if you divide anything by infinity, you get 0. Or we could just plug the 0 joules directly in, showing that we understand that when the atom does not have the electron in it anymore, the electron, relatively speaking, has an energy of 0. So here, our delta E is going to be equal to our final energy for the electron minus our initial energy for the electron, which is going to be 0 joules minus the energy of the n equals 1 orbital. Remember again, E for n equals 1 is going to be equal to negative Rydberg constant times z squared over n squared. So plug in those 1's and we get negative RH times 1 squared over 1 squared, which sure looks a whole lot like negative Rydberg constant. And so our delta E, our energy change for this reaction, is 0 joules minus the negative Rydberg constant, or the Rydberg constant, which is 2.179 times 10 to the minus 18 joules. This is an absorption. That's why it's got a positive energy change. However, for the sake of completeness, I would say that the energy of the photon is equal to the absolute value of the energy change, which of course here is equal to 2.179 times 10 to the minus 18 joules. That guy was positive and therefore an absorption. Now, as a follow-up question, we're asked what type of electromagnetic radiation is required from the reaction. I have not memorized exactly which energies go with which types of radiation, so I would convert my energy into a wavelength because that's my frame of reference that I know. So to answer that second part of the question, I follow the same process as I did on the previous page, which said that the energy of the photon was equal to hc over lambda, and therefore the wavelength is equal to the Planck's constant times the speed of light divided by the energy of the photon. And then I plug in all my numbers, 6.6267070 times 10 to the minus 34 joules per hertz, or joules times seconds. times 2.99795 times 10 to the 8 meters per second, all divided by 2.179 times 10 to the minus 18 joules. Joules cancel, seconds cancel, and I get a wavelength of 9.116 times 10 to the minus 8 meters, which I'd like to convert into nanometers because, again, that's my frame of reference. There are 10 to the 9 or a billion nanometers in 1 meter. Meters cancel, and that gets me 91.16 nanometer radiation. And if visible is 400 to 700, 91 is a little bit less than that. Shorter wavelength light has higher energy, so slightly higher energy than visible is ultraviolet, or UV. And so if you want to excite an electron out of a hydrogen atom, you are going to have to use UV light if you want to get the electron all the way out and not just into a higher energy orbital. What's left over after you do that? The nucleus, which in the case of a hydrogen atom happens to just be a proton. And why do I mention that? Because when we get to acid-base chemistry, we have a tendency to talk about deprotonating things. But that doesn't mean picking protons out of the nucleus. No, that would be crazy. What that means is detaching hydrogen cations from other species, because a hydrogen cation is a proton.